Hello friends, welcome to CEC Live Lectures. Dear friends, in this session we are going to talk in our series on principles of ecology. In our previous session we discussed in detail on ecosystem energetics. Friends, today also we are going to give you the in-depth knowledge on the following topic, and we are going to cover ecosystem energetics, and later on we are going to discuss on nutrients and biogeochemical cycles. For the discussion on the topic, we have with us in our studios Dr. Charu Dogra Rawat. Dr. Charu Dogra Rawat is Assistant Professor in Department of Zoology, Ramjas College, University of Delhi. Dear friends, if you have any question pertaining to today's session or the other sessions we have conducted in the past on principles of ecology, then feel free to talk to us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. Now, I would like to welcome our guest, Dr. Charu Dogra Rawat, once again. Hello, ma'am. Welcome to the lecture.
Thank you. Good afternoon. So, as Geetika has mentioned, we have been talking about ecosystem energetics, and we have talked about the different models of energy and the how it is running. The specific objectives for today's session would be to understand the concept of the carrying capacity and sustainability. We have talked about the concept of, we have introduced the concept of carrying capacity and sustainability when we were doing the population growth. But we'll talk about in terms of energy, how this the concept comes into or plays a role. We'll also understand the concept of the net energy. So we have been talking about the quality of energy, we have been talking about the distribution of energy at various trophic levels, but now what we'll talk about is the concept of the net energy. We'll also understand the energy-based ecosystem classification. So that is basically that based upon the energy distribution, how do we classify the ecosystem? That's what we talk about. We'll also understand the nutrient cycling and biogeochemical cycles. So gradually we'll move about talking in addition to the flow of the energy, we'll also talk about the cycling of the nutrients, and which we termed as the biogeochemical cycles. And in particular, we'll talk about two cycles today, which is the movement of the nitrogen and phosphorus elements in the ecosphere. So starting with the concept of the carrying capacity, I would like to mention here that the reference used is the Odum EP Fundamentals of Ecology, the Indian edition, and it is used only for the educational purposes. Otherwise mentioned, all the illustrations are from this particular book. So we're talking about the concept of carrying capacity when all the available incoming energy is needed to sustain all the basic structures and functions. So that is basically whatever amount of energy that is available for maintaining the system. So that basically talks about when the incoming energy or the production is equivalent to the respiratory maintenance. So when these two energies, the amount of energy which is entering, or which is the energy which is produced is equal to the energy spent for the maintenance of the ecosystem, then that point is called as the carrying capacity. The amount of biomass supported under these conditions is called as the maximum carrying capacity and is referred to as K. So the maximum carrying capacity is when there is an equilibrium between the energy produced and the energy that is utilized. So there is no more energy which is freely available to be passed on, but the energy that is coming or that is produced in an ecosystem is the one which is required to maintain the ecosystem. So at that during those conditions or under those conditions, we say that the ecosystem has reached its maximum carrying capacity, or the capital K. This level, however, is not absolute. It is not the glass ceiling, but is easily overshot when the momentum of the growth is strong. So we will see that when there are or there are conditions when the resources are limiting. So when there is a lot of very enhanced growth is happening, then sometimes they will just shot up over this maximum carrying capacity, or when the resources are really limited, then the maximum carrying capacity would be lower down. At least temporarily it will be pushed down as in the ecosystem. So the optimum carrying capacity is generally what we talk about. So optimum carrying capacity, which is the sustainable over long periods in the face of environmental uncertainties, is lower than the maximum carrying capacity. So we'll look at the growth curve and we will see that the maximum carrying capacity is the maximum number of individuals, for example, an ecosystem can hold. So the amount of energy that is produced is equal to the amount of energy that is spent. But ideally speaking, it tracks the maximum carrying capacity, but tries to stabilize itself at the optimum carrying capacity, which is sustainable over the long time periods in the face of the environmental uncertainties as we talk about. So carrying capacity depends not only on the number and biomass, but also on the lifestyle, that is the per capita energy consumption. So the number and biomass we've already talked about when we talked about the population growth and studied the sigmoid growth curve. But in here it is very important that this carrying capacity also depends upon the per capita energy consumption, which is reflected in the lifestyle of the ecosystem. So this is how the sigmoid growth curve looks like. So you can see this figure, and we have already seen this picture when we did the population growth. It is a typical sigmoid shape. So you can see passing over the time, the size is increasing, the population size is increasing, and it reaches, and this is the point which is called as the maximum carrying capacity. So the size of the individual, generally this becomes, which is called as the asymptote. So this asymptote is the maximum carrying capacity, and this point is called as the point of inflection, and that point of inflection is when the growth is maximum. So this is also referred by the game fish and game managers. The point of inflection is the point of maximum growth, because in here the individuals are very quickly replaced. So even if they harvest it, they are very quickly replaced. So this is called as the point of inflection or the optimum carrying capacity which is there. So this carrying capacity, you can see that the K or the maximum carrying capacity is the upper asymptote that represents the maximum carrying capacity, and this I is the point of inflection, which is also reflected in the lower graph, where you can see that the rate change is maximum. So here it is where the rate of the growth is highest, often spoken to as the maximum sustained yield or the optimum density, as I mentioned by the fish and game managers, because the harvested biomass at this particular point would be the most rapidly replaced at this point. So this is the maximum sustained point, or maximum the point of inflection, or the optimum density as it is referred to as. So this is in relation to, now the maximum carrying capacity is basically where the P will be equal to R. So in here, in terms of energy, so this is the population size which an ecosystem can sustain, because the input energy is equal to the energy which is consumed for the maintenance of this particular ecosystem. So in the fluctuating environment of the world, however, it is difficult to maintain the K, and overshoots are likely to occur. So this is a very common thing, because we do not have a very stable environment and we do not have a very constant environment. So in the fluctuating environment, although we talk about the maximum carrying capacity or the K, but it is very difficult to maintain at that point, and it is the overshooting is likely to occur because of two main reasons. The first is the momentum of growth causes the population size to exceed K. As I have told that a lot of overshooting of this maximum carrying capacity occurs because there is a rate of growth change which is happening, and this momentum causes the population size to shoot or exceed the maximum carrying capacity. And sometimes a period reduction in resources availability temporarily reduces the K. So the K can be increased from the maximum carrying capacity under certain conditions, when reflecting the momentum of growth, and the K can be lower than the maximum carrying capacity, although temporarily, for the periods such as where the reduction in the resource availability is there. Under those cases, for example, the global challenge of feeding people is approaching that point where food needs equal maximum production capacity given current technological, political, economical and distributional constraints. So if we look at this example, then the global change or the challenge of feeding the people is approaching its maximum carrying capacity. Now, any perturbation that reduces crop yield means severe malnutrition or starvation for millions of individual humans living on the brink. So, even if a small change occurs, then this maximum carrying capacity is going to suffer. And, if there is, for example, the reduction in the crop yield, then this is going to, reduce, and there is going to be starvation and there is going to be malnutrition for millions of individuals that are going to occur. So, as it approaches the maximum carrying capacity, it is more vulnerable to any kind of changes that can drastically change the carrying capacity, and it can either overshoot or it can just lower down temporarily because of the changing environmental conditions. So margin of the safety of the maximum carrying capacity level is very small. What does that mean? That basically means that the carrying capacity can change, can either increase or decrease. That margin is very, very narrow. So in terms of longer safety and stability, some level in the range between K and I would represent the desirable carrying capacity level that is sustainable over the long term. So basically the maximum carrying capacity is K, but under certain conditions it can either overshoot or can reduce temporarily, but this particular range is usually narrow, and because of that it can crash or it can just crash down even if it overshoots. So usually for the long term safety and stability, the population stabilizes themselves at any of the points between the maximum and the optimum condition. So you can see that this is called as the range. So at this particular range, most of the ecosystems or most of the populations, they tend to stabilize themselves, and because of the which is termed as the desirable carrying capacity level, because that is sustainable over the long term. So we will talk about the concept of sustainability, which is now we can understand that very much related to the concept of carrying capacity, which we have been talking about. So that way, many natural populations have evolved mechanisms that maintain density at this safe or secure level. So for long term, if it want to sustain itself, it would like to occupy a population size, or the ecosystem would like to occupy something which is lower than the maximum carrying capacity, because the margin of safety at the maximum carrying capacity is really narrow. So it optimizes within this range and regulates itself within that range so that it sustains for a longer period of time. So many ecosystem and many natural populations have stabilized themselves in such manner, and that is very much related to what we talk about in the terms of energy. So this is how the growth occurs, and in terms of the energy that is dissipated, when the entropy is increasing, so to acclimatize or to stabilize that energy production to the energy which is required for the maintenance, the populations and ecosystems tend to stabilize themselves at a range which is optimal or stable for the stable carrying capacity for those particular individuals or the ecosystem, how it is said. So example, we'll take that, for example, study of energy flow in ant colonies reveal about the energetics of scale and carrying capacity applicable to human beings. So let's look at this particular example. So what happens is that in leaf cutter ants, which is Atta columbica, which live in wet tropical forests, they harvest fresh leaf sections from the vegetation and carry them into underground nests as a substrate for the growth of the fungi that provide their food. So they carry these fresh sections of leaves and they carry them to their nests where they culture the fungi that is serving as their food. Now the fungal gardens are cared for and fertilized, just as the human beings, they cultivate the crops for their production, for their consumption. So it's a similar example, and basically it reflects how the energy flow occurs in the carrying capacity which is applicable for the human colonies as well. Now, estimation of energy expenditures for all the major activities within the colony, which was done by Lugo et al. In 1973, revealed that the maximum carrying capacity or the maximum size of the colony is reached when the input of the fuel calories balances the energy cost of the work involved in the cutting and transportation of the leaves, managing the trails and cultivating the crops. So this is very important point. Energy is spent for the energy that needs to be stored. So the estimation of all the energy expenditures, Lugo et al. Revealed that the maximum carrying capacity is reached when the input of the fuel calories balances the energy cost. So whatever energy they are spending for the maintenance of the nests, for the cultivation of the fungi and for the transportation etc. of these fresh cut leaves into their nest, whatever energy they are spending at that point, it needs to be balanced by the energy that is produced. So, at a given time, 25% of the ant population is involved in the maintenance of the, in the nests which are there, and 75% of the ants are actually involved for the transporting the leaves or the maintaining or managing the trails etc. So that kind of a balancing needs to be done, and after that the growth will cease, the colony will just not grow. So when energy input is balanced by the maintenance costs, the colony stops growing. So that is how it is in the case of human beings. When the energy that is used for the energy that is produced by the cultivated crops, that needs to be balanced by the energy that is input for the cultivation of the crops. All the maintenance, the harvesting, the machines, etc., whatever kind of energy that is inputting for the cultivation of a particular crop needs to be balanced by the energy that the crop is providing. And if this balance occurs, then the population then it stops to grow, the colony stops growing. Reward feedback, we have already talked about, is an important phenomena, that the reward feedback to other organisms such as frass deposited by the ants in the forest floor increases the leaf growth, it increases the efficiency and raised the maximum carrying capacity. So when the input energy and the expended energy balances itself, then we say that the population or a particular ecosystem has reached its maximum carrying capacity. After that, it just ceases to grow. But this maximum carrying capacity can be pushed upwards in case there is, for example, a reward feedback. In this particular example, the ants in the forest floor, they deposited frass, which was increasing the leaf growth or increasing the efficiency, and therefore it was pushing the maximum carrying capacity which is there. So this is very important in terms of to understand the maximum carrying capacity concept in the terms of energy that is produced and the expended. So this point becomes very important. Now, estimating this in such a way, the carrying capacity of an agrarian cultivation supported by the subsistence agriculture is not difficult, because it involves the input energy coming from local sources and not from the distant region. So, for example, what we saw in the case of ants, it was basically dependent upon whatever energy that was present locally. So, the energy produced as well as the energy, it is not affected by any distant or far from source of energy which is there. So it's very, it's a kind of a directly proportional thing. The kind of energy, the balancing, the carrying capacity. So to estimate such a kind of carrying capacity is a little easier process. For example, density in the rural countryside in India is a linear function of rainfall, which determines crop yield in the absence of irrigation or other subsidy. So in certain areas, if it is only, the rural countryside, if you are talking about the crop yield, then it is in the linear function of the rainfall which is present. So 10 centimeter of rainfall supports 2 persons per hectare of harvested land, 100 centimeters supports 3 persons, 200 centimeters supports 4.5 persons, and 300 centimeters supports 6 persons. 4 to 5 persons, and 300 centimeters supports 6 persons. So, there is a linear relationship, because in such a kind of environment, we are just talking about the energy which is available by the rainfall and the direct effect of that, which is falling in a linear fashion. There is no auxiliary subsidy here we are talking about. There is no irrigation that is happening. So, in such rural countrysides, it reflects a very, you can estimate the carrying capacity in a very straightforward manner, as done in this particular example, where the density is related to the function of the rainfall. The estimation of the carrying capacity, however, in the urban industrial societies is much more difficult, because such societies are supported by massive energy subsidies imported from afar and often drawn from storage excuse me, such as fossil fuels, underground water, virgin timber, and deep organic soils. So, we have already talked about the energy subsidy. So, if apart from the energy which is present locally in that environment, there are certain energies which are auxiliary or subsidiary which is there and coming from the distant regions also. So, in urban industrial societies, all the involvements are there, such kind of environments are there, and therefore estimating the carrying capacity is a little difficult process, because in that case the carrying capacity, the energy that is produced or the energy that is maintained, there will be a difficulty in estimating all the type of energy, because the energy that is produced might be because of the density or because of the crop yield we are talking about, but the energy expenditure, so there are more than single source for the energy production, and there are more than single source for the respiration or the maintenance, that is energy is there. So, because there are a variety of energy that is involved in the source process, there is a variety of energy that is utilized at the respiratory process. So, in that case, the estimating the carrying capacity becomes a little difficult. So, we can, however, looking at the energy consumption or energy utilization or energetics of an ecosystem, we can estimate the carrying capacity of a particular population or of a particular ecosystem which is there. So, as I said, this concept of carrying capacity is very much related to the concept of sustainability. When we are talking about the concept of carrying capacity, that is the maximum number or the maximum size a population or a particular ecosystem can contain. If we talk about, for example, in the number of individuals, so the number and biomass which is maximum it can contain, that is the carrying capacity. But however, it tends to stabilize itself, because there comes a term which is called as sustainability. So, sustainability is directly related to the concept of carrying capacity, and it is defined as maintaining the natural capital and resources. So, what we talk about natural capital is that all the different kind of natural sources which are resources which are available, the populations or the ecosystems do not tend to utilize all these. So, they kind of keep a track of the resources which are present, so that they stabilize at a point where these resources can be available for a longer time. So, if these natural capitals or resources, they utilize in such a manner so as to utilize them for a longer period rather than reaching their maximum carrying capacity and consuming them, for example, in a very short period of time. So, that's how the concept of sustainability crops in. Now, this should be used as a guide for the future development, because the present environment might be able to carry still there is a still there is a provision for the ecosystem to carry more of the individuals. For example, but one should keep it as a guide for the future development, the sustainability aspect, because if we reach up to the maximum carrying capacity, then we tend to, because the resources then will become limited, or we will consume the resources which are available too fast, we tend to fall short or lesser than the maximum carrying capacity. So it's much better to stabilize at something which is lower than the carrying capacity, so that it can be used for a longer period of time, or it can be sustainable. So in human affairs, for example, in the long term, sustainability may be more effectively understood and dealt with in terms of the optimum carrying capacity concept. So, this is what we are trying to understand here, that although an ecosystem can sustain a larger number of individuals, the individuals tend to stabilize themselves at an optimum carrying capacity rather than the maximum carrying capacity. And this is so because it is more sustainable. So the amount of resources or the amount of energy, which can be produced or which can be utilized, the amount of resources which are present will be available for a longer period of time, rather than when we utilize all these resources to the maximum that is present at a given point of time. So in human affairs, it is very, very important, and for that, very many new strategies and technologies have been developed, such as the use of windmills to generate electricity, illustrate how natural capital, in this case, for example, wind, can be used to generate economical capital such as the electrical energy. So when we talked about the maintaining natural capital and resources, so this is our natural capitals, the wind, the solar energy, all these are the natural capitals which are there. If these natural capitals are utilized, and generate the economical capital for the benefit of individuals, then it will be more sustainable rather than using and utilizing the resources such as fossil fuels or other resources to the maximum, so that they will deplete and they will end, and therefore after having this maximum carrying capacity, the number of size will drastically reduce. So it's better to use these natural capital and resources so as to maintain or generate the economical capital as it is mentioned. So we also talk about another concept which is called as the net energy concept. Now it takes energy to produce energy and to recycle materials. Some of the energy produced by any conversion system must be either fed back or supplemented by outside energy to maintain the system. So when we talk about this energy, we have to understand that there is something which is called as the net energy produced, because that any energy which is produced or any energy which is taken up by an individual, it also needs an energy to be produced. So we have to keep in mind about this particular diagram, that to produce the net energy, the yield must be greater than the energy cost of sustaining the conversion system. So for example, in this case, A is the yield, and energy source, whatever energy we are getting, there is an energy which is input for the sustaining this particular yield. So when we talk about this net energy, and this net energy, to produce this net energy which is termed as A here, the yield must be greater than the energy cost of sustaining the conversion system. So for the energy source, harnessing this energy for utilizing, for example, harnessing the solar energy for the production of crops. So this energy needs a conversion system. For example, all the kind of energy which is utilized in agriculture. So this yield should be greater than the energy which is utilized for producing this yield. Then this net energy is, being produced. If the input energy is much more than the energy that is yielded, then in terms of energetics, it is a loss of energy that is happening. So that is not a very, that is not how the ecosystem works. So the yield should be much more, and therefore designing for the future practices and sustainable practices, one should keep in mind that the yield of energy should be more than the energy which is necessary for producing that yield to be utilized by the conversion system. So in energy sources for humans, for example, it is not about how much oil and natural gas is present under the surface of the land and seas, but how much will be available when on the energy penalties associated with energy dissipation, such as drilling, protection of human health and pollution prevention have been paid. So whatever energy is produced from the oil and natural gas, it should consider the energy that is expended to produce that energy, and that net energy should be in the positive, should be in a plus sign. So we do not have to talk about that how much oil and natural gas is present, but how much energy we are able to, how much net energy we are able to produce after putting the energy for this conversion system which is there. So we'll continue with this a little later.
With this note, thank you, and thank you so much for giving us this productive session. Friends, you're requested to be with us. We are going to be back after a short break and would be continuing further. Thank you for watching us. Hello friends, welcome back to this session. Friends, you know that today we are talking on ecosystem energetics once again, and we are trying to cover this following topic. Friends, after covering this topic, we are going to talk on nutrients and biogeochemical cycles, and for the discussion we have with us in our studios Dr. Charu Dogra Rawat. Dr. Charu Dogra Rawat is Assistant Professor in Department of Zoology, Ramjas College, University of Delhi. Friends, if you have any set of questions in mind, feel free to talk to us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. You are just requested to call in the last 10 minutes. Now, I would like to welcome our guest, Dr. Charu Dogra Rawat, once again. Hello, ma'am. Welcome to the lecture.
Thank you. So coming to the last leg of ecosystem energetics, we just classify the ecosystems on the basis of energy. So we have talked about the flow of energy, we have talked about the production of energy, we have talked about the various energy efficiency, the quality of energy, we have talked about the, we have related the concept of this energy flow with the concept of the carrying capacity, the concept of sustainability, we have talked about the net energy concept also. So the last thing in this energy ecosystems is to classify the ecosystems on the basis of energy, and as such, based upon the source and the level of energy, there are 4 different categories in which the ecosystems are classified. So there is an unsubsidized natural solar powered ecosystems. So unsubsidized natural solar powered ecosystems basically refers to the ecosystems which are solely provided energy by the sun. So sun or the solar energy is the only source of energy that is available or utilized by these particular ecosystems, and they are not provided energy by any subsidized or auxiliary systems. The examples include the open oceans, the upland forests, grasslands and large lakes. So as you can see, then the power level which we generally talk about, which is the amount of the annual energy flow, it is generally low in these areas. So in this natural solar powered ecosystems, because there are other limiting factors such as the nutrients and the water. Because of these limiting factors, the power level is a little lower in certain ecosystems, but the organisms have adapted themselves to live in such low nutrients and low water availability and produce the energy. So these are the kind of ecosystems where, but they are very important. Although the diversity, although the number of organisms is lower, but these ecosystems are very important because they are the ones that harness the natural capital we have been talking about. So that natural capitals, they purify the air, or they are the ones which are very important because of the large extent. If we talk about open oceans, these oceans, 70% of the earth is water. So in 70% of earth is covered by these oceans. So because of the large extent, even if at the power level they are lower in production of energy, but they are very, very important ecosystems. And in there, they are the ones, and when we talk about the future sustainability, or for future, any policy that needs to be made for the maintenance of these ecosystems, these are the ecosystems that need to be harnessed, or these are the ecosystems that need to be kept in mind for developing any kind of, the source or the production that needs to be there. So in these areas, the number is lesser, but the production is very much important because of the large extent which is there. So such are the unsubsidized natural solar powered ecosystems. These systems constitute the basic life support models for the spaceship Earth, the natural capital which we have been talking about. The second and third category falls under the subsidized solar powered ecosystems. So there the primary energy source is the sun, but apart from that there are other auxiliary or subsidized sources of energy which are present. They can further be divided into the natural subsidized solar powered ecosystems, and then because they are the human subsidized solar powered ecosystems. So natural subsidized ecosystems are such as the tidal estuaries or the some rainforests. So in coastal estuary, they are very much rich in the production of energy as compared to the watersheds around them, or as compared to those areas are the ones which are very much rich. The tropical rainforest, some of the rainforests, they are much richer than the surrounding land or the watersheds as we have been talking about. So these naturally subsidized solar powered ecosystems produce much larger amount of energy. As you can see here, 20,000 kilocalorie per meter cube. So that is the power level which they are producing. These are the naturally productive systems of nature that not only have high life support capacity but also produces excess organic matter that may be exported to other systems or stored. So these are the natural ecosystems, naturally subsidized solar powered ecosystems which are very rich in energy, where the energy has been increases. Now humans also started to intervene or provide such auxiliary or subsidized energy sources for increasing the production or the yield of the ecosystem. For example, the agriculture, what they started on the land, or aquaculture, what they started in the water. Those are the food and the fiber producing systems supported by auxiliary fuel or other energy subsidies that are supplied by the humans. So agriculture, when the crop production is started by the humans, or the plant growth, the cultivation of crops is started. So they provide the auxiliary energy source which is there. In the natural energy source, they take the wind energy, the tidal energy, but in here the energy is provided by the human beings to increase the yield or increase the production of an ecosystem. One thing to notice here is that the naturally subsidized solar power ecosystems and human subsidized, in both cases the power level is similar. As in here you can see that it ranges from 10,000 to 40,000 annual energy flow which is there in both the cases, and this is because the energy production might be similar. Humans must have provided the auxiliary sources and raised the yield up to the level by which the natural ecosystems also produce by using the auxiliary or subsidized energy sources which is there. The difference, however, is in the extent of the distribution of these energy. When we talk of humans, then humans tend to produce energy only in the production of food. They tend to accumulate all the energy, whatever energy they are subsidizing to increase the crop yield, they want to convert it into food. However, when we talk about the natural ecosystems, they tend to distribute this photosynthesis activity to many individuals which are there. So they tend to increase the diversity of the population. So that is the difference between. So the production of energy or the power level might be similar, but the distribution of the extent of energy varies in these two, naturally or the human solar powered ecosystems which are there. Then comes the fourth category of the energy based classification of ecosystem, which is the fuel powered urban industrial systems. So humans again have intervened in here, and they have produced, they utilize the fuel energy, or those are the are wealth generating, although also pollution generating systems, in which fuel replaces the sun as the chief energy source. So these are not solar powered, it just not supplements, but it kind of replaces the solar power, and primarily the energy sources, the fuels, the fossil fuels which are there. They are dependent on the other classes for ecosystem for life support, the food and the fuel. So they cannot work in isolation. They have to depend upon the other ecosystems. But the yield, as you can see, is much high. The annual energy flow is, in the orders of magnitude what you can see in the human subsidized solar powered or unsubsidized natural solar powered ecosystem which is there. So the energy, the production, the power production is much higher in the fuel powered urban industrial systems, but it does not rely on the natural capital which is present, and then it tends to these ecosystems such as the cities or the suburbs or the industrial parks, they tend to utilize this fuel energy for the higher production of the power, but then it needs to be dependent upon the other ecosystems for the food and the fossil fuels, because they are generally utilized for production of power which is used for many other resources than just the food which is there. So this is how the classification of ecosystems occurs when we talk about in the terms of energy base. So as I said, the more concentration needs to be, or the more focus of the future guiding principles should be on the unsubsidized natural solar powered ecosystems, because of their extent, and the measures or the policies need to be drawn to harness these particular ecosystems. We are utilizing these to the maximum because of its high power production, but then they will be depleted, and then, as I said, that after reaching the maximum carrying capacity, it will just crash down. So the possibility is that if we explore such kind of ecosystems, the natural capital or harness, then we can increase the power level for the it is more sustainable in terms of the stability of the ecosystem what we talk about. So this is how the classification of ecosystems basis on the energy we talk is there. Now coming to that, we have talked about the energy flow in an ecosystem. Another thing that moves in an ecosystem is the material, the nutrients and the material. And we will talk about these biogeochemical cycles, what are the types of biogeochemical cycles, and we'll take upon the examples of biogeochemical cycles, that how certain elements are circulated in a particular ecosystem which is there. So chemical elements, including all the essential elements of life, tend to circulate in the biosphere in characteristic pathways from environment to organisms and back to the environment, and these are termed as the biogeochemical cycles. Now, movement of these elements and organic compounds that are essential to life are often designated as the nutrient cycling. So you can call them material cycling, nutrient cycling, but usually because they are important for the maintenance of life, all these essential elements, human beings are unique because they are the only ones which needs around, which utilizes almost 40 of the elements which are present. So they utilize these elements and they circulate these elements from the environment to the organisms and then back to the environment, and therefore this kind of biogeochemical or the nutrient cycling keeps on occurring. Now, each nutrient cycle in general can be divided into two compartments or pools. One is termed as the reservoir pool, the large, the slow moving, generally the non-biological component. As the name suggests, it is the reservoir pool. So that will be the pool where the nutrient or the element which we are talking about tends to accumulate or stored. It is the non-biological component. And the labile or the cycling pool, which is a smaller but more active portion that is exchanging rapidly between the organisms and their immediate environment. So that is more of the labile or the cycling pool we are talking about. So based on this reservation pool where they are located, the biogeochemicals can be of different types. So in ecosphere as a whole, if we look at, biogeochemical cycles fall into two basic types. One is termed as the gaseous types, in which the reservoir is in the atmosphere or the hydrosphere. So we will see that the nutrients tend to accumulate either in the air or in the hydrosphere, and when from there the nutrients are utilized and then circulated between the organisms and the immediate environment, then they are termed as the gaseous types of biogeochemical cycles. For example, the nitrogen, we will talk about. So nitrogen is available in the atmosphere. There are, the nitrogen comes into the organisms and their immediate environment. So it keeps circulating, but the reservoir pool is the atmosphere where it is present. So such type of biogeochemical cycles are gaseous types. Then there are the sedimentary types, in which the reservoir is in the crust of the earth. For example, we will take one example of the phosphorus biogeochemical cycle. So phosphorus is not available. It is present in the air, but it is not available to the organisms, as the most of the phosphorus that is utilized by the organism comes from the sedimentary beds. So it is from the earth crust. So such types of biogeochemical cycles are termed as the sedimentary types of biogeochemical cycles. Now again, I would like to emphasize at this particular point that energy in some form must be expended to recycle the materials. So energy needs to be expended. The nutrient cycle by themselves do not run. They run on the energy that is needed to be expended for the nutrient to be cycled in the ecosystem which is there. So, if we look at this, then the elements in nature are almost never homogeneously distributed, nor are they present in the same chemical form throughout the ecosystem. And that is why the conversion system takes place. And apart from this conversion system, the flow of nutrients take place, because they are not homogeneously distributed. One, there will be a maximum concentration, and other, there will be a lower concentration, but the organisms which are living in the lower concentration will then draw the elements from the higher concentration hubs and utilize them. So there is always a nutrient movement that is occurring, and when this occurs between the organisms and the environment, it is termed as the biogeochemical cycles. So, and the energy needs to be expended for that. Therefore, in this particular diagram, what we do is, we have talked about the universal energy flow model. We superimpose this universal energy free model by the nutrient cycling or the biogeochemical cycle which is there. So you can see here that this black portion is the biogeochemical cycle. Now energy flow is a unidirectional flow. It flows from one end to the other end. However, you can see that the biogeochemical cycle is a cycle. It is a circle. It is circulating. So it's not in a single manner, it's not a single flow, but it circulates. It's a kind of a cycle which is there. Energy, however, when it goes to the next level, it is never available to the previous level. So the energy which is going, it's always it's a single flow. There can be more channels, but it's just a unidirectional flow what we talk about. However, the nutrient cycling is nutrient movement is cyclic in nature. So it is a circular in nature, and it can be returned and gained again. So in here, in the biogeochemical cycle, what we see, then this black portion is the nutrient pool. This half is the nutrient pool. This nutrient or the reservoir pool is also sometimes referred to as the unavailable pool and is indicated by the box labeled the nutrient pool. The cyclic portion is referred to as the available or the exchange pool, is designated by the circle going from autotrophs to heterotrophs and then back. So you can see that this particular circle which is going on here is the one which is going from the autotrophs to the heterotrophs. So this cycling portion is here. This is the reservoir box, the nutrient pool which we are talking about. So one important thing is that the terms unavailable and available or exchange pool is relative. It's not that the energy which is there in the nutrient pool is not available at all. It does leak out in small fluxes and come into the cyclic portion, but that is referred to as unavailable pool or available pool in a relative term. So this nutrient pool, this is the hub, and this is the circulation or the the leakage of the flux, and then the cycling of the nutrients which keeps on occurring, making the biogeochemical movement of the nutrients in a cyclic manner rather than whatever energy, and the energy needs to be spent for this movement to occur. So that is also one important aspect. So we'll take up two examples here. One of the cycling of the nitrogen to start with. In general, we'll study 5 different cycling biogeochemical cycles, but today we cover only 2, which is the cycling of the nitrogen and the cycling of the phosphorus. Now, nitrogen cycle is a very important example and is an example of very complex, well buffered, gaseous type of cycle. So let's understand how this nitrogen cycle looks like. So because the source of the nitrogen or the nutrient pool is basically the atmosphere, therefore it is termed as a gaseous type of cycle, and it is a complex cycle. As you can see that many different parts or many different things are involved in here. So most of the nitrogen which comes into the plant protoplasm and is stored as the proteins and nucleic acids is utilized at the expense of the energy and converted into the what is called as the ammonia. So it can be released in the form of urea and ammonia, etc., and by the heterotrophic organisms also. So many of the plants and the dead decaying organisms, the decomposer protoplasm is also there. So the conversion of the nitrogen into what is termed as the nitrites and the nitrates occur. This conversion is carried out by the nitrifying bacteria. So there are nitrification that occurs. So in the plant, whatever amount of nitrogen is stored, for example, in the leguminous plants, they contain these bacteria in their root nodules, which have the capacity to fix atmospheric nitrogen. So these kind of nitrogen fixation, as we can see, called as the biofixation, is done by a variety of bacteria. So they tend to fix the atmospheric nitrogen in the form of ammonia. The plant protoplasm, the plant also which can fix these atmospheric nitrogen, or by other physical mechanisms such as the rain or lightning, etc., this nitrogen can be fixed also. So all these nitrogen which is available in the form or in different forms such as ammonia, ammonium, nitrites and nitrates, these all are available, and they are the nitrifying bacteria converts it into these particular and they return it back. The denitrifying bacteria then return these nitrites and nitrates back to the atmosphere. There is a smaller cycle also which is running in between these forms of nitrogen and the producers or the organisms which are there. So ammonium or the nitrites and nitrates, they can be taken up by the plant over the expenditure of energy. They can be used to synthesize the blocking building blocks of these particular organisms. So they can be used to synthesize the proteins, they can be used to synthesize the nucleic acids. So this is a small cycle again which is running. So in the plant protoplasm, whatever proteins and nucleic acids are there, so the major part is that the atmospheric nitrogen is fixed or biofixed in the form of ammonium. This ammonia is then converted into ammonium nitrites and nitrates by the nitrifying bacteria. These nitrifying bacteria are also present in the root in the nodules. Even these nitrogen fixing bacteria are also present in the nodules of the plants, and therefore fixes it in the form of ammonia, which is there. This can go back to the atmosphere by the activity of the denitrifying bacteria, or they can also go back and cycle again in this particular smaller ones. The atmospheric nitrogen can also be fixed, as I said, by the physical components, which is the rain or the lightning, etc. But you can see that this particular going back of the nitrites and nitrates into the atmosphere, you need to expend the energy. This energy expenditure can be by the breakdown of the proteins, etc., which is present in the plant, so the expenditure of energy, or by the breaking down of the few fossil fuels which are there. So expenditure of the energy. So these Nitrobacter and Nitrosomonas, these nitrifying bacteria expends energy to release this amount of nitrogen back to the atmosphere. Then when the fossil fuels are also burnt, then also this nitrogen goes back into the environment. So this is how the nitrogen basically circulates. Now important aspect is that the nitrifying bacteria, they break down this they need to break down this triple bond and to convert it into 2 molecules of ammonia. So they also expend energy to do so. So the energy needs to be expended for the fixing of the nitrogen. The energy needs to be expended for the fixed nitrogen to go back into the atmosphere. So all this is again energy driven, and therefore we superimposed in the last diagram the biogeochemical cycles on the energy flow in an ecosystem. So the energy flow needs to be there for this nutrient cycling to occur. Now, initially the nitrogen fixation were done by the rhizobium. It was established that there are certain microorganisms such as rhizobium and clostridium. Rhizobium converts aerobically and clostridium converts anaerobically. Then there were azobacter which was there, and then there were cyanobacteria which were there. So these were the nitrogen fixation organisms, but now more and more organisms tend to be said, such as the rhodospirillum, which is also converts nitrogen or fixes the nitrogen, which is a purple bacteria. Then there are pseudomonas like soil bacteria. So a lot of pseudomonas like soil bacteria also fixes nitrogen. Then a lot of actinomycetes, they are filamentous bacteria. A lot of actinomycetes have been isolated that can fix the nitrogen. Even in the oceans, there are certain species that can fix the nitrogen. So all the microbes, they can fix the nitrogen. A lot of microbes, all the prokaryotic system, they can fix up nitrogen. The plants, and then there is a relationship between, all these bacteria, for example, tend to accumulate there are many bacteria which tend to accumulate the root nodules of the plants. So plants gives a very congenic environment for these bacteria to grow in the rhizosphere, and these bacteria then fixes the amount of nitrogen which is there. So this nitrogen is then brought into the ecosystem, and then by utilizing this nitrogen, they can be they can go back, the nitrogen can go back into the atmosphere which is there. Now in atmosphere, 70% of nitrogen is present. So initially when this biogeochemical cycling was of nitrogen used to be studied, nitrogen used to be mentioned as a limiting factor, because there were not many bacteria which were known to be fixing this particular nitrogen. Now what they talk about is the detrimental effects of the increase in nitrogen. Now apart from the many the natural populations that fixes the nitrogen, human intervention is also increasing much more nitrogen into the environment. The nitrogen that is applied as the fertilizers, it just leaches, it just goes into the environment which is there. So the nitrogen component is increasing in the environment. So, and these are related, they are just the amount of bacteria which are present are not able to fix this natural environment which is there, and because of that it is creating a lot of problem. The increase in the nitrogen is creating the very toxic effects which are there. Nitrogen is there in the water, it cannot be removed. So they are now creating a lot of toxic effects which are also causing a problem. So for any future decisions that need to be made, the cycling of nitrogen needs to be done. Although the humans have come up with artificial systems of nitrogen fixation, they have developed root nodules in corns, etc., for the nitrogen fixation to occur. But still, there's a large amount of toxicity that is happening. So the global nitrogen cycle depicting reservoir pools of fluxes and per year. So this particular diagram tells about how in the terms of amount of nitrogen that is fixed at the different levels. So you can see this is given expressed in the billions of metric tons per year. So in the human sources, now more and more of nitrogen is also accumulating in the environment because of human activity, and because of these anthropogenic activities there are a lot of runoffs which are happening. So the amount of nitrogen that is fixed by the biological systems, or for the biofixation that can be utilized to convert it into some organic compounds, there is a lot of free nitrogen which is present in the environment. So you can see here that in atmosphere how the changes occur, how much amount is fixed on the land by the denitration, and how much then it is returned back into the environment, how much is just running off, and how much by the physical components also it is utilizing. So these are the two different ways by which we are studying this particular cycling of the nitrogen environment. So this was one biogeochemical cycle which we took as an example, and we'll talk about the different biogeochemical cycles in our subsequent sessions. Thank you.
Thank you, ma'am. Thank you so much for giving us this session. Friends, you are requested to write to us at info.cec@nic.in if you have any question or if you wish to give your feedback. We will upload this lecture on YouTube soon. So keep watching us, keep writing us. We are going to meet again and would be discussing more. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.